very simple design, works fairly well. Obviously, there's a lot more backups than that, but yeah, control rods are very, very important to controlling chain reactions. To summarize that, the control rods are made of cadmium or boron. Those are elements which absorb neutrons and slow down or stop the nuclear chain reaction. Okay, now how does this look like in a nuclear power plant? This looks very simple. This is a general diagram of a nuclear power plant. And as you notice, it looks very similar to the coal-fired plant that we've been looking at before. Here's the turbine. Here's the generator. There's steam coming in to spin the turbine, which spins the generator, which makes electricity. And then the steam is condensed and run back in to be boiled again. There's a big cooling tower to turn the steam back into liquid water. By the way, the cooling towers that you see in pictures of nuclear reactors, that's not the nuclear reactor. The steam that you see coming out of cooling towers is not radioactive steam, is not radioactivity. It's just an area where steam has been condensed back into water again, just like they are in many coal-fired plants or oil-fired plants. Okay. Now, the nuclear reactor, this is where it's different. We're using a nuclear reactor and heat from nuclear reactions instead of a pile of burning coal to produce the steam. Now, the big difference between a coal-fired plant and a nuclear power plant, well, three differences. One, there's a nuclear reactor. We just said that. The second difference is that there's control rods in here, which can be dropped into the reactor to stop the reaction if you need to shut the thing off. The third difference is that there are two loops of water, okay? Because the way we get heat out of the reactor is by circulating water through the reactor. The reactor boils water. Now, the problem with that is that the water coming out of the reactor is carrying radioactive material and radioactive waste, which is really, really dangerous. It's really poisonous stuff, and we don't want it to get out in the environment. So in America and in most of the world, when they build a nuclear reactor like this, they put it inside of a concrete dome. I should have had a picture of one of these here, but I forgot to do it. But you've seen these. I mean, like you've seen pictures of millstone. It's this big concrete cylinder with this huge, thick concrete lid. Or in some nuclear plants, it's, well, here, yeah, I do have one. These are where the reactors are. These are domes of concrete with the nuclear reactor inside them. And this concrete is like 5 feet thick, and it's steel reinforced, incredibly strong stuff. And it's basically sealed up. There's very few holes in that. So the nuclear reactor and all of that water that cools the nuclear reactor is kept inside that very, very strong dome. So that if one of these pipes breaks and starts spilling out water that's carrying radioactive material, it stays in the dome. It doesn't get out into the environment. Okay, so what they do is they use the hot water from the reactor to boil another circuit of water. So they use superheated steam, highly compressed water like a pressure cooker, to boil water, and that steam from that second tank of water, that's what goes out through a pipe that goes through the containment dome to the turbine and the generator. Okay, now they have radiation detectors inside this heat exchanger, and if one of these pipes cracks, one of the pipes from the nuclear reactor cracks, they close the valve and they stop any water and radioactive material from getting outside the dome. So that's the safety thing. So they call this the first circuit. The first circuit is a circuit of water which circulates through the reactor but never leaves the containment building. And then the second circuit is water that circulates into the containment dome and takes heat away from the first circuit. But the water in the second circuit never comes in contact with the nuclear reactor, so it's not carrying radioactive material. And that's how they do it. Okay, um, let's wrap this up here. What's good about nuclear energy? Good things about nuclear energy is that you get energy on demand whenever you need it. You can turn this thing on and turn it off to produce more electricity or less electricity when you need it. And this means that nuclear energy can be used to fill gaps in the wind and solar energy base. Okay, so we can get most of our energy from wind and solar, but what do we do when the sun goes down, or when the wind stops blowing, or when everybody goes home from work and turns on their air conditioners and their microwave ovens? Well, then you boost the nuclear energy output and you fill the gaps left by wind and solar. So we could have an energy system where most of the energy comes from wind and solar, and we just use a little bit of nuclear energy to fill the gaps, which is a good thing. And this, by the way, that is the reason that there are a lot of people saying that we should take another look at nuclear energy and strongly consider building nuclear power plants again, um, because of the next advantage, which is nuclear power plants do not produce greenhouse gases. We're in a world where global warming and climate change are real problems, and nuclear energy will not contribute to global warming. And that's huge. Another nice thing about nuclear power plants is they can be built anywhere. It's not like hydroelectric dams or geothermal plants where you're limited by the geography of where you can build these things. We're limited by geology. You can build nuclear power plants wherever you want them. Um, Usually that's going to be far away from a city in case there's an accident. You don't want to poison the population with nuclear waste. But yeah, there's really no limit to where these things can be put. Finally, there's lots of uranium in the world. This isn't an energy source that we're going to run out of anytime soon. Technically, nuclear energy is a non-renewable energy source because it does depend on uranium, but uranium is a very common stuff. And at the rate that we use it right now, the rate that we use nuclear energy right now, um, there's enough uranium to last well over 1,000 years. Much more, a longer lived supply of uranium than there is of coal or natural gas or oil. Be around for a long time. Um, And to fill the gaps in wind and solar energy, we really would not need significantly more nuclear energy than we have right now. Certainly not in the United States. We'd be able to get by with the same amount of nuclear energy that we have right now if all the other energy that we had was from wind and solar. Now, other countries in the world don't have as many nuclear power plants as we do, so the worldwide use of nuclear energy would probably go up if we went to powering the whole civilization on the entire planet Earth from a combination of wind, solar, and nuclear. Um, so that would reduce the amount of time that the uranium would last. But there are other elements besides uranium that also work. And there are ways to turn uranium 238 into useful fuel to extend the lifetime of that supply. So yeah, good things about those are good things about nuclear energy. Now, what about bad things about nuclear energy? Um, the huge, bad, horrible thing about nuclear energy is that it produces nuclear waste, which is highly radioactive, very deadly stuff that stays deadly for a long, long time. It lasts about 100,000 years. So if we have nuclear power plants, we have to come up with a way to store and seal away this nuclear waste for 100,000 years. That is a huge problem, and it is not one that anyone wants to minimize. That is a real problem, and that is the largest objection that people have to nuclear power plants is the problem of what to do with nuclear waste. There's also the potential for nuclear accidents. What happens if one of these nuclear power plants has an accident and the containment building ruptures and spews out a bunch of radioactive waste into the countryside? That's what happened in Japan in Fukushima after the tsunamis a couple of years ago. The design of the plants was such that they didn't imagine a situation where they would lose electrical power to cool these things for more than a couple hours. It didn't occur to them that they could lose every nuclear power plant in an entire complex of nuclear power plants, and that they could lose the entire electric grid over a large section of Japan, so that there was no way to provide electricity to their to the cooling pumps. when they built those plants in Fukushima, they had backup systems for their backup systems for their backup systems, and they all failed because of the magnitude of that disaster. So when you build a nuclear power plant, there is a potential for nuclear accidents. We'll get into that more tomorrow, but this is another significant thing. If you're going to be building nuclear power plants, you want to be really, really sure that they're not going to explode like Chernobyl or like Fukushima and render a large section of your country or your state uninhabitable for decades at least. Another disadvantage of nuclear energy is that they're expensive to build, although less expensive than you might think. And the bottom line here, and this is kind of the the root cause of our objections to nuclear energy, is people are simply afraid of nuclear energy. And it's for good reason. I mean, like I say, the problem with nuclear waste and the potential of nuclear accident, this fear is somewhat justified. The question is whether or not we want to invest some research into solving these problems, because the benefits of nuclear energy are really, really good in this time of global warming and climate change. So yeah, tomorrow we'll talk about nuclear waste and the bad things about nuclear energy. That's what we'll talk about next time. Now there is this another slide here that I want to show you. We'll get it out real quick. I believe it's on this one. I meant to put it in this slide deck, and I seem to have not done it. Is to give you perspective about how much energy we get out of uranium. And there's a nice graphic that we had. Let's see. So yeah, this is the one right here. So one uranium pellet, when they make uranium fuel to put in nuclear reactors like Millstone, they make it into small pellets. This is the relative size. So this is a dime, so they're about the size of a dime. It's about the size of the metal piece on your pencil that holds your pencil eraser. That's about how big these pellets are. And there are thousands, tens of thousands of these pellets loaded into a nuclear reactor when they fuel one of these things up. Now, each individual pellet has as much energy, will release as much energy as about 3 barrels of oil, which is about 150 gallons of oil or gasoline, or that's about as much energy as a ton of coal from just one little chunk of uranium, or as they say, 17,000 cubic feet of natural gas. Well, how big is that? That's one of the large natural gas or propane tanks that you see by people's houses sometimes. It's actually, it's a little bit larger than that. It's more like what you'd see in a commercial, like a factory. They don't use tanks this big for people's houses. Not only that, but that's only the first time you use this pellet. Once a lot of the uranium-235 in this pellet has been used up, has been triggered and turned into krypton and barium, what happens is the krypton and barium and the other nuclear waste products, those elements soak up neutrons so that you can't get any more energy out of this pellet, even though there's still a lot of uranium-235 in this pellet. So what they can do is they can pull this pellet out of the nuclear reactor, extract the uranium-235, most of which is still in that pellet, to make new pellets, and then use the same fuel, put it in another nuclear reactor, and get another bunch of energy out of it. And from a single pellet, you can reprocess it many times, like half a dozen times at least, um, and get more energy out of it every time until all of the uranium-235 is used up. So yes, gigantic amount of energy from a very, very small package in a nuclear reaction. And in this process, it doesn't produce any carbon dioxide, doesn't produce any acid rain producing chemicals, doesn't contribute to global warming. And these are some pretty strong arguments in favor of going into this. Anyway, so let's wrap this up here. Um, what did we learn today? We learned about nuclear energy. We learned what isotopes are and what that term means. We learned what fission is, which is splitting nuclei into smaller pieces, and why we get energy from it. We also learned about how much energy we get, which is a whole bunch. We learned what a nuclear chain reaction is and how we control them using cadmium and boron control rods. And then we got into good and bad things about nuclear energy. Today was mostly about good things. Next time we'll get into nuclear waste, why it's dangerous, and what is done with it and what can be done with it. All right, have a great rest of your day, and we will see you next time.